All right, hello, welcome to this week of our Math 2414 weekly reviews. This week we're going to go ahead and cover trig substitution and partial fractions. So let's go ahead and get started with our trig sub. So whenever we do trig sub, what we're going to go ahead and do, so let's actually go ahead and give an example first. Let's say we are given an integral that looks something along the lines of this. Well, we can't do u sub because, so normally if we have like a root, we try to do u sub, but the thing is we don't have like any sort of just x multiplied times that. So we're going to have to figure out something else. We could try to do integration by parts, and we could go ahead and let's say let our u be the 9 minus x squared to the 1/2. Our dv is dx. Our du would then be 1/2 times 9 minus x squared to the negative 1/2 times negative 2x. And then our v would just be x. So if we went ahead and put that in, organize that, we would be getting x times the square root of 9 minus x squared minus the integral. We have this 1/2 is going to, and the 2 and the 1/2 are going to cancel, so we're going to have our x and then our other x to get us a negative x squared over 9 minus x squared, that's a square root, dx. Well, we still can't solve that, so we're just kind of stuck for right now. So that brings us to the topic of trig sub. So with that, so trig sub it is based on what is called change of variable. Yeah, process is called change of variable, and you guys have actually seen change of variable before. You have actually done this when you did any sort of u sub, because essentially what you did whenever you either integrate or derive, what you essentially, like when you integrate with u substitution, and in a way, if you kind of think about it, kind of when you do chain rule, when you derive, you essentially are, but especially when you integrate, you are trying to turn your integral from terms of x to terms of u. Well, trig sub is actually kind of similar, except in this case, you are going from x to theta. So there's a few different types of trig sub that we can do. We have, oh, where's my pen at? Okay. All right, so we have a few different types that we have. So it kind of just depends on the format of your problem. So we have three different formats that we could do. We could have a squared minus x squared. We could have a squared plus x squared. And we could have x squared minus a squared. And in this case, a is just a regular constant. So let's go ahead and see what this is. So this is kind of our format that we have in our problem. This is going to be the substitution itself in this column. And then over here, we're going to go ahead and show why it works. or the formula it's derived off of. So if we have a squared minus x squared, what we're going to do is we're actually going to say that x is equal to a times sine of theta. And if you want to be technical, our angle is in between negative pi over 2 and pi over 2. And the reason why this works, and really the reason why all of them work, is based off of the idea of Pythagorean identity. So y'all are probably a little bit familiar with this. So essentially, the main Pythagorean identity that most people are familiar with is essentially sine squared of theta plus cosine squared of theta equals 1. Well, the idea is that we want to get the format 1 minus sine squared of theta equals cosine squared of theta under that radical. For our a squared plus x squared, we are going to do x equals a times tangent of theta. And once again, our domain is going to be between negative pi over 2 and pi over 2. And of course, this one has to be, this one is not like less than or equal to, this one's just less than because tangent is undefined at those angles. And the Pythagorean identity this one works with is that 1 plus tangent of theta equals secant squared of theta. And then lastly, we have our x squared minus a squared. So in this case, we're going to do x equals a times secant of theta. And this time, our theta is either going to be between 0 and pi over 2, or pi and 3 pi over 2. And this one is just a rearrangement of that one just above it, so where we know that secant squared of theta minus 1 equals tangent squared of theta. And also, just as a quick little side tip, if you ever have trouble memorizing some of your Pythagorean identities, memorize your main one. And then you can divide by either sine squared of theta or cosine squared of theta on both sides. So for example, if we divided by cosine squared of theta, we would get sine over cosine would be tangent squared of theta. Cosine over cosine is 1. And then 1 over cosine would be secant, so secant squared of theta. And once again, you can do the same thing if divide by sine squared. However, that one we don't typically use as much, but this is just a neat little trick just to help you memorize it in case you ever forget it. All right. So now let's go ahead and do a practice problem. So we're actually going to go ahead and go back to the problem we just looked at. We are going to integrate square root of 9 minus x squared. So in this case, we see in 9, so what we can do is we know 9 is a perfect square. So we can actually rewrite this as saying that we have 3 squared minus x squared dx. So we have an a squared minus an x squared. So therefore, we can go over here and say that, let me actually go ahead and change colors. We can go ahead and say that x is equal to 3 sine of theta. And similar to when we do u sub, whenever we do u sub, you have to figure out what your du is. The same thing applies here. You have to figure out what your d theta is. So therefore, if x is 3 sine of theta, your dx is going to be 3 cosine of theta. So now what we do is we just go ahead, and anytime we see an x, we plug in 3 sine of theta, and we plug in 3 cosine of theta d theta for our dx, just like with U sub. So what we're going to do is we're going to go ahead, we're going to have our 3 squared minus, we're going to get 3 sine of theta squared times 3 cosine of theta d theta. We can go ahead and pull out a 3 squared in here and just rearrange to where we can get 3 squared times 1 minus sine squared of theta times 3 cosine of theta d theta. All right, so now we take this, so now we can go ahead and substitute in a cosine squared right here. So now if we take the square root of our 3 squared cosine squared of theta, we're going to get 3 cosine of theta times 3 cosine of theta d theta. Combine this, we're going to get 9 cosine squared of theta d theta. All right, so now we're almost there. Now the issue is we can't really, if we could change cosine squared to 1 minus sine squared, but that still wouldn't help us. So we're actually going to have to go back to our handy little power reduction formula. So last week we learned that cosine squared of theta is equal to 1/2 times 1 plus cosine of 2 theta. So anytime you have a cosine squared of theta that you can't get rid of with U sub, you can go ahead and use your power reduction formula. And it won't come up as often, but there is also a power reduction for sine, just in case y'all ever come across that, which is the same thing, just you change the sign in the middle. So what we can do is we can go ahead and plug in this cosine squared of theta formula to where we get 9 times 1/2 times 1 plus cosine of 2 theta I would go ahead and pull out that 9/2. Or you can either pull it out or distribute, either way. You can go ahead and pull it out. I'm going to pull it out and say that we have 9/2 times 1 plus cosine of 2 theta d theta. And what I would also do is split this up into 2 integrals, just to make this a little easier to work with. When in doubt, split into 2 integrals. So we have 9/2. So if we integrate d theta, we're just going to get theta. If we integrate cosine of 2 theta, well, we know we're going to get a sine, or 2 theta, and whenever we do kind of like a U sub reverse chain rule, we have to put a 1/2 out here. And then, of course, we have a plus c. So now if we go ahead and distribute, we have 9/2 theta plus 9/4 sine of 2 theta plus c. So now we're in theta. We're integrated. We have to be able to get back to x, though. So earlier we said that x is equal to 3 sine of theta. Well, if we divide both sides by 3, we're going to get x over 3 is equal to sine of theta. And we know that sine of theta is equal to opposite over hypotenuse in a right triangle. So what we're going to do is we're going to go ahead and draw our triangle. We have our theta here, so therefore our opposite is x. Our hypotenuse is going to be 3, and our adjacent is 9 minus x squared. And you know you're on the right track because you want to see like that original root in the problem whenever you build your triangle. So now it's just a matter of trying to plug and chug. But we also have one other problem. We have a sine of 2 theta, but the thing is we can't really solve that with our triangle. So we actually have another trig identity that it's really important to memorize. That identity is going to be sine of 2 theta is equal to 2 sine of theta cosine of theta. So we can go ahead and plug that back into our formula to get us 9/2 theta plus 9/4 times 2 sine of theta cosine theta plus c. All right, so now we're getting close. Let's just go ahead and change that to a 9/2 while we're at it. All right, so let's go ahead and solve. So right here we just have a plane theta, so we can't really use our triangle for that, but we can use our original identity to solve for that. So if we know that x over 3 is equal to sine of theta, we can go ahead and take the arc sine of both to cancel out that sine. So therefore that would cancel out. So we know we have that theta is equal to arc sine of x over 3. So 9/2 arc sine of x over 3 plus, we know we're going to have 9/2 times our sine of theta, like we said, is going to be x over 3. And our cosine is going to be our adjacent over our hypotenuse. So it's going to be 9 minus x squared over 3. We can go ahead and cancel these 3's out with the 9 to where we get 9/2 arc sine of x over 3 plus 1/2 x square root of 9 minus x squared plus c. So I'm sure, as you can tell, these problems are kind of long. I will try to do as many as I can. We are also trying to fit in some partial fractions today, so hopefully we can get to some things. Let's see, how many practice problems do I have? I have 1, 2, okay, I have 3 more, I think. All right, so now let's go ahead and try another one. In this one, we are wanting to integrate dt over the square root of 4 plus t squared. All right, so we see an a squared plus a t squared, so therefore we're going to use our tangent identity. So we're going to say that tangent The square root of 4 is going to be 2 tangent of theta. Therefore, our dt is going to be 2 secant squared of theta. All right, so now let's go ahead and start plugging our identities in. All right, so we know our dt, like we said. Oh, don't forget your d theta. Your d thetas and your dt's are very, very important when you do trig sub. Just keep that in mind. I know normally that's kind of like not a huge deal if you kind of forget it, but trig sub, you really have to make sure you take your dx, dt, du, d theta, whatever that is, you have to take that into account. So yeah, I know it's easy to kind of forget, but just make sure that like whenever you're doing your work that it shows up. So we know our dt is going to be 2 secant squared of theta d theta. And then we know down here we are going to have, I'm going to go ahead and turn 4 into 2 squared. Our t squared, so if we square 2 tangent of theta, we're going to get 2 squared tangent squared of theta. We can go ahead and pull out that 2 squared, or just rearrange it, to where we get 2 squared times 1 plus tangent squared. So then now we can substitute in secant squared right here. And now we have 2 secant squared of theta d theta over 2 secant of theta. Well, right now we can go ahead and cancel out these 2's, and we can cancel out this secant and one of these secants. So we are left with the integral of just secant of theta d theta, and we can go ahead and just use our rule that we memorized a couple weeks ago and just say that we have the natural log of secant theta plus tangent of theta d theta. Why did I put a d theta? We're done. Okay. So now we have our integral done. Now it's just a matter of converting back to terms of t. So like we said earlier, we have our right triangle. We draw our triangle, and we said that t is 2 tangent of theta. Therefore, t over 2 is tangent of theta, which is equal to opposite over adjacent. So we have t, a, and then the square root, 2 right here, of 4 plus t squared. All right, so now we just go ahead and plug everything in. So we still have our natural log. We know that secant of theta is going to be hypotenuse over adjacent. So we're going to have square root of 4 plus t squared over 2. And of course, tangent is opposite over adjacent, so t over 2. And then plus d, and then we are done. So now let's go ahead and look at another one. In this one, we have x times x squared minus 9 dx. So we could do our trig sub and say that since we have an x squared minus an a squared, that we have x equals 3 secant of theta. But, oops, we have an x squared and an x. If you see that, you should be thinking u sub. So sometime this would hold, so for here we could actually instead say that u is x squared minus 9, du is 2x dx over 2 over 2, 1/2 integral u to the 1/2 du. And then it's just basic u sub. You just get u to the 3/2, 2/3, 1/2 plus c. This one was just to really just show, sometimes it's just always just to kind of keep an eye and just think through all of your strategies that you have to solve a problem. So this one, yes, it very obviously looked like this was like one of like your key, like this is a very, like it looked like it would just be like a simple trig sub. It's like the perfect form. You don't have to do any weird stuff with it. But it would still be a lot quicker to just go ahead and use our u sub in this instance. So yeah, just moral of that story is just, yeah, just always kind of just think through all of your strategies and just, this is actually a really big part of, especially for your first exam in integral cal. It's just always trying to keep like a tally and kind of always just think about your strategy for solving different ones, which methods are easier, which methods are harder, and just kind of figure out how to attack a problem. So let me see. Okay. All right, so yeah. So now let's think about what happens if these aren't always super black and white. In this one, we are going to be integrating x plus 1 times the square root of x squared plus 2x plus 2. Well, if we look at this, we can't really do a u sub because the derivative under our root would be, well, our u sub isn't quite obvious, but we could maybe do it. For this example, I'm going to do a trig sub just so we can kind of see like how to actually do this. A lot of steps in this, you could do a u sub, but this one I'm going to go ahead and do like everything as a trig sub, just so you can kind of get an idea of how to approach trig sub problems that don't always seem like in the super obvious x squared plus a squared format. So what we can do under here is we can take our x squared plus 2x plus 2. Well, we can go ahead and let's bracket this off. And let's go ahead and try and see what happens if we try completing the square. So we have an x squared plus 2x, so therefore our constant would be 1. We have our plus 2, and of course we need to subtract 1 because we just added a random 1 in there. So where we now have x plus 1 squared plus 1. So this is where things get kind of interesting. So this is where things can get kind of interesting. So we now have a couple spots where we have an x plus 1. So right here, we could kind of do a u sub right here. So where we can say that we have u is equal to x plus 1, and du is dx. So if we go ahead and plug this in, we get u square root of u squared plus 1. So once again, like right here, you could definitely do a u sub right here. But like I said, I kind of want to just go ahead and show how this kind of works whenever you have to do multiple changes of variables. So I'm just going to go ahead and keep doing trig sub, but like if you were like on an exam or something, I would do u sub and be done with it. So then what we're going to do is, so now I now have a u squared and then a 1. So now what we can do is we can take that and turn that into a trig sub. So where we can say that u is tangent of theta and du is secant squared of theta, d theta. Also, just another tip, especially if you have a problem where you're going to do multiple changes of variables. I know on an exam you may not be able to do that, but if you're doing homework or something, or just practice problems, I would color code every change of variable you have. That way it gets less likely to kind of get mixed up with everything. So that's just like a little tip that I have, especially with trig sub, since I know it can be like really, really messy at times. So we have our u is tangent of theta, our square root, once again, tangent of theta squared plus 1 times secant squared of theta d theta. All right, and then now we can go ahead and get to work. We have our tangent squared of theta plus 1, which is going to go down to secant squared. All right, so then we have tangent of theta. We have a secant times a secant squared, so secant cubed of theta d theta. So now this goes back to last week whenever we just did trig, just normal trig integrals, not necessarily trig substitution. So right here, let's actually go ahead and bracket off a tangent secant and then the secant squared. So now right here, we are actually now in a good spot to do another u sub. So right here, I'm actually going to call it v since we already have a u elsewhere. We are going to say that v is equal to secant of theta, and dv is secant tangent d theta. So now we have v squared dv, which then goes to 1/3 v cubed plus c. So then we now are back down to 1/3 secant cubed of theta plus c. So now we can go ahead and draw our triangle with this. We had established earlier that u is equal to tangent of theta. Actually, let me go switch colors on this. Yeah, so u is equal to tangent of theta. And we know that tangent of theta, once again, is opposite over adjacent, and we can treat this as u over 1. We have our theta right here, so therefore we get a u of 1 and a square root of u squared plus 1. So we know that once again, secant is equal to hypotenuse over adjacent. So therefore, secant of theta is just the square root of u squared plus 1. We can cube that. So now we have 1/3 times u squared plus 1 to the 3/2 plus c. But remember, we had also said earlier that u was equal to x plus 1. So now we just plug in an x plus 1 for u. And you can be done, and you can also compare that to just 1/3 x squared plus 2x plus 2 to the 3/2 plus c, which is what you would have gotten if you did u sub much earlier in our problem. So now let's go ahead and look at partial fractions. So when we do let's say we have a problem such as this. We need to integrate 2x plus 1 over x squared plus x minus 2 dx. Well, this one is actually not that bad. We can do a u sub. We can say that u is x squared plus x minus 2, and our du is 2x plus 1 dx. Well, we have our u, we have our du, and of course we have our dx. So we're good to go. That would just be du over u, which gets you the natural log of the absolute value of u plus c. And then you just plug in your x. And you're done. But what happens if we turn that 1 into a 2? We can't do our u sub anymore because then we don't have the right du. So that brings us to the idea of, so then we have to perform a process called partial fraction decomposition. Okay, so when we do partial fraction decomposition, it's based on the idea of whenever you add two fractions with different denominators, you have to find a common denominator to add them together and then kind of, make that one fraction. Well, essentially with this is we're trying to actually break the big fraction down into the smaller fractions that are easier to deal with. So for this one, we had 2x plus 2 over x squared plus x minus 2. Well, if we go ahead and factor and turn the denominator into factors, we can say that is equivalent to 2x plus 2 over x plus 2 times x minus 1. Now, we could always look to see from this point if we can go ahead and cancel anything out, but right now we cannot. So what we have to do is we need to try to break this down into smaller fractions that are easier to integrate. So what we do is we say that we know our two bottom pieces have to be x plus 2 for one and x plus 1 for another, but we don't know what the numerator is, so we're just going to call them a, some constant a, some constant b. So now what we do is we can go ahead and now almost work backwards in a way for sort of how you would find a common denominator. So we'd cross multiply and use that to figure out what a and b, use the numerator to figure out what a and b are. So essentially what we do is we now say 2x plus 2 is equal to a, and then we have to cross multiply with x plus 1 plus b, which was cross multiplied with x plus 2 with, oh, I've had a typo in here. Good thing I caught that before we got really far into the integral. That is an x minus 1. All right, and we have our x plus 2 right here. So now what we do is we can go ahead right here, and this is the easiest way to do this, is plug in values that would eliminate one of the two variables. So when we do this, if we plugged in an x equals 1, it would eliminate that a from the equation, allowing us to solve for b. So if we plug in x equals 1, we can get 2 times 1 equals plus 2 equals a times 1 minus 1 plus b times 1 plus 2. So then therefore we can get 2 plus 2 is 4 equals 1 minus 1 is 0, so a is out, and then 1 plus 2 is 3 times b. And then we can say that b is equal to 3 over 4. Similarly, we can say that we can also look at this and have an x equals -2. If we plug that in, we get 2 times -2 plus 2 equals a times -2 minus 1 plus b times -2 plus 2. We get a -4 plus 2 is -2 equals -2 minus 1, -3a, and then -2 plus 2 will cancel out to 0. We can then solve and then say that a is equal to 2/3. So now what we do is we go ahead and we can plug this back into the original, and we can now say that 2x plus 2 over x squared plus x minus 2 is equal to 2/3 over x plus 2 plus 3/4 over x minus 1. Now this is actually in a much easier spot for us to integrate. So if we go ahead and do our integration, we can do this. We can either do it all at once, or I like to go ahead, personally like to split it up into two integrals. when I do partial fractions and then look at each part. So if we go ahead and integrate, we can go ahead and pull out this 2/3 right here, just because constants can sometimes get in the way and make things hard, and make patterns harder to find. So we have 1 over x plus, so we're integrating 1 over x plus 2. Well, if we kind of do a quick mental u sub to where we let u equal x plus 2, du is dx, so therefore this would just be a simple log. This would just be our natural log rule for integration. And then, of course, don't forget our 2/3. Similarly, if we look at our other half, we have 3/4 out in front, 1 over x minus 1. Once again, we can do a mental u sub. U is x minus 1, du is dx. We get du over u, which gets us the natural log of x minus 1 plus c. So then therefore our final answer, that's a 2/3. Wait, which one? Let me just double check my math real quick. Okay, yeah, we're good. I was just having to double check my math real quick. Okay, I was right the first time, yeah. So then we get, our final answer is 2/3 natural log of x plus 2 plus 3/4 natural log of x minus 1 plus c. So now let's go ahead and try one that's just a little bit different. All right, so in this one, we want to integrate x cubed minus x plus 3 over x squared plus x minus 2 dx. So if we look at this, we can factor the bottom, we can't factor the top. And also, another important thing to note with this one is that the power of the numerator is bigger than the power of the denominator. So when this happens, the first thing we actually need to do is go ahead and do long division to simplify this down. So what we're going to do is we're going to put x squared plus x minus 2 into x cubed. I'm going to leave kind of a big blank for that, 0x squared minus x plus 3. All right, so in order to get us to that x cubed, we need to multiply this whole piece with x. So we're going to get x cubed, x squared, and then 2x. We put our x up here. And then, of course, we are going to subtract that piece. So minus x cubed minus x squared plus 2x. When we do this, we get negative x squared plus x plus 3. All right, so now we have in x squared and the negative x squared, so we're going to have to multiply times -1, but you're going to write that up here. and then we have to subtract. So if we're subtracting a -1, we're really just adding that initial piece that we had to begin with, which will get us 2x plus 1 for our remainder. So therefore, we can go ahead and we've turned this into x minus 1 plus 2x plus 1 over x squared plus x minus 2 dx. So the next thing we need to do is first we're just only going to pay attention to this piece right here. We'll come back to the rest of the integral, but for right now, we need to break this fraction down into something we can actually integrate. I mean, you could do u sub, looking at this one, you could do u sub if you wanted to for this one, but I'm just going to go ahead and once again kind of work through another partial fractions problem just so y'all can get like more exposure on how to do these. So for this one, we have 2x plus 1 over x squared plus x minus 2 is equal to x plus 2 and x minus 1 in the denominator, and of course we keep our 2x plus 1. Now we have to break this up into our two fractions with our different pieces. All right, we can now go ahead and solve for our a and b. So of course we're going to keep our 2x plus 1 is equal to a times x minus 1 plus b times x minus 2, x plus 2. So now if we plug in x equals 1, we get 2 times 1 plus 1 equals a times 1 minus 1 plus b times 1 plus 2. We get 2 plus 1 is 3, 1 minus 1 is 0, 1 plus 2 is 3b, b equals 1. And of course over here we could do x equals -2. We would get 2 times -2 plus 1 equals a times -2 minus 1 plus b times -2 plus 2. -4 plus 1 is -3. -2 minus 1 is once again -3. And then 2, -2 cancel out. -3 equals 3a. A equals 1. So now we have, so now we can say that this is for sure equal to 1 over x plus 2 plus 1 over x minus 1. So now let's go back to our full integral. We had x minus 1 from our long division, and then from our partial fractions we had 1 over x plus 2 plus 1 over x minus 1 dx. All right, so now if we go ahead and look at this, if we integrate that x, we're going to get 1/2 x squared. If we integrate the -1, we get -x. Right here we have 1 over x plus 2. For that, I would once again mentally use sub, where u is x plus 2, gets you du over u, so plus natural log of x plus 2. And then once again, same thing, to where we get natural log of x minus 1 plus c. And if you wanted to try doing it with u sub, you would essentially get the same thing, just a slightly different format. Or if you just want to clean this one up a little more, you'd still, to where you can combine these logs to where you multiply your x plus 2 and x minus 1 to get you back to x squared plus x minus 2 plus c. All right, so now let's try another one. All right, so for this one, we are wanting to integrate x squared plus 3x minus 4 over x cubed minus 4x squared plus 4 dx. All right, so we see that the power on denominator is higher, so we don't have to do long division. That's great. That's just, you don't have to do that extra step. So now it's just a matter of doing our decomposition. So if we go ahead, that's a 4x, I was about to say. Always double check your notes, always double check your math for just miswriting stuff. So now we can go ahead and start breaking that down. So we see we have a common factor of x throughout our denominator. So we get x times x squared minus 4x plus 4. And then we can break this down again. That x squared minus 4x plus 4 is actually going to be x minus 2 squared. So things are actually a little different if one of our factors is squared, or if it's raised to just any power. So what we do right here is we still kind of do our basic premise whenever we do our partial fraction. So we know that we have an a over x. But now if we have a fraction, like one of our factors, raised to a power, you have to start with, you have to have your highest power, so x minus 2, and you start with your highest power squared and then just keep going down until you get down to 1. So in this case, it's pretty easy. So where you just have x minus 2 squared and just x minus 2. If that was, say, to the 4th, you would have one that would be like b over x minus 2 to the 4th, c over x minus 2 cubed, d over x minus 2 squared, e over x minus 2. So now we have our 3 pieces, and now let's go ahead and get to work on trying to solve for our a, b, and c. So we have x squared plus 3x minus 4 is equal to a, and all that they need is just, they have our x and they just need our x minus 2 squared plus b, they have the x minus 2 squared, so they just need the x. And then our c, which only has one x minus 2, so we're going to multiply it times x, and another x minus 2. All right, so now let's see what we have. Looking at this, there's not really a good way for us to just kind of do the method we were doing earlier, to where we just pick a number to get like kind of cancel some things out. Instead, what we have to do, because essentially the big thing is that we wouldn't be able to solve, we wouldn't have a good number to solve for c. So instead, what we can do is we can go ahead and expand all of this out. So first we can get expand your x minus 2 squared, so x squared minus 4x plus 4 plus bx plus c times x squared minus 2x. So now what we do is we expand out even further. So we get ax squared minus 4ax plus 4a plus bx plus cx squared minus 2cx. So now what we need to do is go ahead and figure out a good way to solve for this. So what we can do is we can actually group everything out with like a common power of x. So what we can do is we can say, let's take our x squared. So we have ax squared and cx squared. So we know that x squared is equal to ax squared plus cx squared, because there's nothing else I could, because bx couldn't contribute to that. We have to have everything with the same power. So therefore, we can kind of convert this into a system, into part of a systems of equations, to where our coefficient for x squared is just 1 equals a plus c. We can then combine our just x to the 1, so where we have 3x is equal to negative 4ax plus bx minus 2cx. And then over here for systems of equations, we can say that 3 is equal to negative 4a plus b minus 2c. And then lastly, we just have 4a just chilling by itself. So now let's go ahead and get to work on solving our systems of equations. So the easiest one, of course, we have is our 4 equals 4a. From here, we can just say a is 1. So now what we do is we take this, a equals 1, and the next easiest one to solve would be this one. So we can now say that 1 is equal to 1 plus c. Right, give me just a second. Okay. I think I had a math error in my notes earlier, so we're going freestyle right here. This is why you always double check your signs when you write things down. Oh wait, no. No, I was right, actually. Yeah. That's a -4. That's a -4 right here. Yeah, that's a -4. I was right. -4, so that A is -1. So yeah, we get 1 equals -1 plus C. So then we can go ahead and solve for C to get us 2 equals C. So now we can go ahead and plug our A and our B in here. We know that 3 is equal to -4 times our -1 plus B minus 2 times 2. 3 is equal to -4 plus B equals 4, plus 4. These cancel out. 3 equals B. So therefore, our final form is going to be and go ahead and set up our integral, is going to be -1 over x minus 3 over x minus 2 and that's the negative, wait. Okay, yeah. That is a plus. That one is a plus. I was like, I knew there was an error in my notes. It was just in a different place than I thought it was. But it doesn't change it. It doesn't change much, so we're okay. Plus 2 over x minus 2. All right, so now we just have to go ahead and solve each of our integrals. So like I said, especially when you have different coefficients and different sign changes, I typically like to break them down. So for our first one, I'm going to pull out our -1. 1 over x dx is just negative natural log of x. 3 times 1 over x minus 2 dx is equal to our 3 natural log of x minus 2. And then, of course, we have our 2, pull out our 2. 1 over oh wait, this one's squared. This one's squared. Okay, there we go. We're good now. So yeah, we can go ahead and pull out our 3 right there for B, for our second term. And we get 1 over x minus 2 squared dx. Now, this one, we still do a U sub, but this one it's just a little different, just because we have a power of -2 to -1. So for this one, we get U is equal to x minus 2, du is still dx. We go 3, u to the -2, du. negative 3u to the negative 1 plus c. All right, and then for our last one, we pull out our 2, which will get us 1 over x minus 2, natural log of x minus 2. So now we just have to combine all of our pieces to get us natural log of x minus 2 minus our natural log of x minus 3 over x plus 2 plus c. All right, and then I have just one more example for you before we go. So for this one, we want to integrate x plus 1 over x times x squared plus 1. So this one is actually a little different from all the other ones we've done because we cannot factor that x squared plus 1. That just has to just chill there. So right now, our bottom piece is as factored out as it can get. But because we have a quadratic in there, that actually kind of changes our approach just a little bit. So if we have our x plus 1 over x times x squared plus 1, we still have our x, and we still have a 1 with an x squared plus 1. The difference here is that we're still going to keep an a over x. On our x squared plus 1, though, we will instead be using a bx plus c. So whenever you do partial fraction decomposition, but if you have something linear on the bottom on your denominator, your numerator has to be a constant. If you have a quadratic, then your numerator has to be at most linear. You may sometimes get a constant. You have to kind of solve your decomposition in order to see for sure. But you know for a fact that is the highest power it can have. That is why we have an x plus c. So now let's go ahead and set it up. We have x plus 1 is equal to a times x squared plus 1 plus bx plus c times x. So now, once again, this isn't really a good one to where we can just plug and chug numbers, especially because there's not, that x squared plus 1 will never equal 0 at any point. So we're going to have to go ahead and do another systems of equations. So once again, we're going to go ahead and expand everything out to where we get ax squared plus a plus bx squared plus cx. All right, so now let's go ahead and solve for everything. We have 0x squared we have a 0x squared for our ax squared plus bx squared, so 0 equals a plus b. We then have a cx, our x is equal to cx, so therefore 1 equals c. And then we lastly have Our last term is just our a, which is our constant, so 1 equals a, 1 equals a. So this one's a lot easier just because we didn't have as many terms. So if we can just go ahead, we know C, we know A, plug A in here, and we can get B is equal to -1. So now it's time for us to go ahead and reset up our decomposition again. So we know that we have 1 over x plus -x plus 1 over x squared plus 1. So now if we integrate, once again, let's split up into 2. This piece is actually fine. We know that one is just ln of x. This piece, our second piece, is not as fine because once again, we can't do our U sub, and it's kind of wonky. But before we start panicking, we can see that we have 2 terms in our numerator. So what we can do is we can actually go ahead and split that up into 2 different terms. We can go ahead and split this up and say that we have -x over x squared plus 1 plus 1 over x squared plus 1. All right, so now let's go ahead and look and see what we have. Right here, let's go ahead and split up into 2 integrals. For this one, we actually have a pretty easy U sub. We can say that U is x squared plus 1, du is 2x, dx divided by 2. And right here, we can go ahead and factor out a -1/2, u to the -1, and then we can get -1/2 natural log of u. Now we have to take a look at this part. So although I don't think I didn't go over it in this lecture, your profs probably have covered this a little bit. This is actually another common identity. So our integral for 1 over x squared plus 1 is actually going to be arctangent of x plus c. So that's just one you have to memorize. I know, I think in your book there should be a chart for like all of your inverse tangent identities. So I would go ahead and look at that. I'm sure you could probably do some trig sub and try to like figure that out by hand, but it's easier just to memorize the formula rather than spend all that time trying to reverse engineer it. So for this one, our final answer is going to be the natural log of x plus arctangent of x minus 1/2 times the natural log of x squared plus 1 plus c. All right, so that is all I have for you today. So good luck on everything you have coming up, and I will see y'all next week. Do you have, oh yeah, if you have any questions, like before we go, since we still have a couple minutes, you can go ahead and put them in the chat. Right, so that is actually all I have for today. So if there are no questions, then everyone's free to go.